From the following data, calculate the lattice energy for sodium oxide. Note that the oxide formation equation is provided starting from gaseous species and its formation energy. The delta H of formation is also provided for this same reaction. But in addition, there are other data related to sodium and also to oxygen. So, in this exercise, through this resolution, we are going to learn how to use all this information to calculate this lattice energy. Well, initially we should keep in mind the following. Lattice energy is energy released by definition when an appropriate number of gaseous ions are brought together to form an ionic solid mode. So, starting from this definition, we will need to use a reaction in which we will have gaseous species combining to form sodium oxide. The lattice energy can be represented by this equation, 2 sodium plus gaseous state plus oxygen 2 minus, forming Na2O. We will then need to manipulate the question data, the information provided, to obtain this final equation. Let's go. Initially, we are going to use the equation that was given in the exercise. It's the formation equation, but we're going to invert it. Let's write Na2O, leading to the formation of solid sodium 2 and gaseous oxygen. As we reverse the reaction, so the value of delta H is also reversed in terms of sign. It was minus 414. We are going to use it then, save this result enthalpy of 414 and a positive value. Okay, but here in this equation we have sodium in the solid state and oxygen is already in the gaseous state. But sodium will need to pass into a gaseous state and then be converted into an ion. Oxygen is already in the gaseous state, but it must also be converted into the Na2O ion. So let's start working with sodium first. Solid sodium, we need to move to the gaseous state. Change of physical state from the solid state to the gaseous state, sublimation. And then we're going to go back. We're going to use the information given delta H of sodium sublimation. So putting solid sodium to gaseous sodium delta H 108 kilojoules per mole. This sodium needs to be ionized, so we're going to use its ionization energy now. In order to turn sodium into more sodium, we'll need to remove an electron. The corresponding value is 496 kilojoules per mole. Very good. So, for sodium we already got where we want it to be. However, there is one detail. As in the equation for 2 moles of sodium, here we will also need to write, in step 2, multiply the value of delta H by 2 and multiply the ionization energy by 2. Let's now move on to oxygen, Na2O. We need to provide an energy in order to break the oxygen-oxygen bond. And so we're going to use dissociation energy here. As this energy is also given by mole, we will multiply by half to make the proper adjustment. Very well, now we only have O oxygen in the gaseous state, no more molecular oxygen. But we need to convert it to ion. Na2O, we will need to supply an electron that will be corresponding to its first electron affinity. Okay. See, the first energy is minus 141 kilojoule, and then we give the second ion whose corresponding value for the second electron affinity is 790 kilojoules per mole. Perfect. If you look closely, these are partial equations that we've written, and the sum, in quotes, of these partial equations will give us a global equation, which will be exactly solid Na2O, forming 2Na plus O squared. So, when we account for all of these energies calculated in these steps, we will have a value of 2520 kilojoules per mole. And just one detail is missing. See that the equation we want to obtain, in order to calculate the lattice energy, is the inverse of what we obtained here. Well then, let's invert. We obtain 2 sodium plus Na2O minus Na2O and invert the previously obtained sign. And then yes, finally we will have arrived at the lattice energy for the sodium oxide compound.